Hello guys, back with another video. It's been a while, so back with another power electronics video, and this time we're going to be doing something exciting and new. As you can see from this generated clip art, we're going to be doing an inverter, and in the past we've done the square wave inverter, and that was pretty good. It was fully discrete. We generated the square wave, and yeah, square wave inverter is good and all, but these days all the loads they need sine, right? Our 230 volt RMS grid, that's the one. It's sinusoidal, right? So square waves are not really good. They have a lot of harmonics, and the devices are not really that tolerant of square waves. So we do need a sine wave inverter, or as they call pure sine wave inverters these days. So basically, we're going to be doing a scaled down model of that, as always, a proof of concept, and how we exactly generate the sine wave from a microcontroller. This is not discrete, because doing this in discrete would be a little hassle. It's just done better these days in digital. You have much more control, and it's much more advanced, more precise, and everything. So yeah, it's going to be microcontroller based. So we don't have a battery today. I have my supply. We'll just use the supply. Of course, later I'll upgrade it to a battery, but nevertheless, so as always, just the most basic thing is, yeah, the inverter converts your DC direct current into AC bidirectional, and you can use that to power your loads or whatever. So what we're going to be doing today is that this uses pulse width modulation if you do it in the microcontroller domain. So basically there are many kinds, but the one which we're going to be covering is the most common one, which is more commonly known as SPWM, or sinusoidal pulse width modulation. And what you basically do here is, if I just give you the gist of it, you have your reference sine wave, right? Digitally you sort of, you want your, let's say you want a 50 hertz sine wave, right, for our Indian grid. So let's say you take this 50 hertz sine wave as your reference at like, let's say it's normalized. That means it's between plus 1 volt and minus 1 volt, just for computation purposes. And what you do is you take a triangular carrier, and this is going to be high frequency, and generally in inverters they try to keep it above 20 kilohertz at least, because below that you can hear it and it hums and all. So because our human range is up to 20 kilohertz, so what you do is you take your triangular carrier and generate it at, say, 25-30 kilohertz or something like that, and you basically compare this reference sine wave with your high frequency carrier, and what results is this sort of a pulse train which looks like this. And even though I just picked this image off the web, you can roughly see that when the amplitude of this reference is very low, like here at this point it's just practically zero, right? Because it starts, you can see that there's just the pulse width, it's basically zero, you could say, because the amplitude is zero here, right? And let's say here it becomes sort of higher. It's still lower than the carrier, because the carrier amplitude is currently at the peak, whereas your reference is here, right? So again, the output is still zero till that point. And now at this point, basically now your reference has gone higher than your carrier, so you get a pulse width of, let's say, this much. Then as it goes on, at the maximum point, even though this one doesn't show it very well, uh, at the peak of your reference, basically you'll have the maximum width. So what happens is it starts increasing, first zero pulse width, then slowly increasing towards the middle, that means your peak. You will have the maximum pulse width, then again it begins decreasing, and yeah, that's how it basically does. And yeah, this is illustrated. If you try to do it in the discrete way, this is literally a comparator, a op amp comparator. So yeah, you give your reference and the oscillator generates the ramp or triangle, in this case, yeah, triangle, and yeah, you get the output as your pulse train. And what you can do is you can drive MOSFET, or a set of MOSFETs with this. And the most famous topology again, and the most classical one, is this full bridge, or you can call it edge bridge. Those are the two names which are most famous. And why it's called that way, as you can see, it is because your load, you have your DC, right? As I said, it converts DC to AC. So you have your DC bus here, and you have these four MOSFETs arranged in this way, so it sort of looks like a edge. So that's why it's called an edge bridge. It's as simple as that. And your AC output will be across the midpoints of, this is one leg and this is one leg. So this is a half bridge, this is a half bridge, it together it makes a full bridge. So your load is basically going to be between this and this. And if I try to just show you how that bidirectional part comes, let's say you turn these two switches on, right? Then the current would flow like this, and you would basically get a plus voltage across your load. And now if you turn these two switches on, the current would flow like this. So then you would get a minus voltage, negative, if you measure with this with respect to this. So that's how the AC is generated from your DC. And even within SPWM, there are two. You have bipolar SPWM, which I just described to you, where you alternatively turn the diagonal switches on. And with this you can generate a sine wave which goes between plus VDC and minus VDC, so directly from this top to this bottom. And that's good and all. And a more advanced one is unipolar, and there what you do is like how I showed you in this image, right? That you generate first, you compare one reference with the carrier, right? In unipolar, what you do is you generate two references. So you have your original, the yellow color is the same one as before, and basically you take another reference which is 180-degree phase shifted. What that means is that now the zero crossing of this is at this point, right? Now the zero crossing of this one will be at this point, so it arrives 180 degrees later, so basically one half cycle later. And same as before, you compare this reference, the yellow one, with your carrier, as well as you compare your blue reference with the carrier, and you will get two sets of PWMs there. You'll get two pulse trains. And what you do is now you drive, let's say you have reference 1, you generated one PWM. What you need to do is you need to drive the MOSFET below this with the complementary of that, which means if this one is on, this should be off. So that's what complementary PWM is. And you, as illustrated many times in my past videos, you do need dead time, which means you need to keep both the switches off for a certain amount of time, because MOSFETs are not ideal devices in real life. They cannot turn on and off instantly. So you need to make sure to give some dead time, so that this, if both of these turn on at the same time, shoot through will happen, and yeah, you'll have a short circuit. So as long as you handle the dead time, you feed the comparison of carrier, the reference one with the carrier to this one, and the complementary of that to this one, and the comparison of the reference 2 with the same carrier to this one, and the complementary to this one. So that is what is known as unipolar. And the benefit of that is you basically get an output which is between plus VDC, 0, and minus VDC. So that 0 level is added, sort of you can say it's three levels instead of two levels in the bipolar. So you get, yeah, of course you get better waveform quality, and also filtering becomes easier, because as you know, the output of this, if I just show you the image, the output of your inverter, which is going to be between plus VDC and minus VDC, it's gonna roughly look like this in case of unipolar, and I'll show it to you in hardware later. But basically, filtering unipolar is easier, because if you view the voltage across your load, it's going to be at the double of your carrier frequency. So let's say your carrier frequency is 25 kilohertz. In the case of bipolar, you will have to filter out 25 kilohertz and so on, the multiples of that. Whereas in unipolar, they'll be at 50 kilohertz and so on, double of it. So if you choose a filter with a cutoff of, let's say, 5 kilohertz, it can filter out 50 kilohertz and so on much better than 25 kilohertz and so on. So you get a much better sine in the end. But yeah, you need to, the only difference is it's sort of more complex, since you need to generate 4 PWM signals instead of only 2 in case of bipolar. So now that the basic theory, now that you know that, we'll go into the code. And yeah, I've done this on the STM, same as before, the Nucleo board. And the code is not that tough actually. The very good thing about STM is they have the advanced timers which have built-in dead time, and you can directly configure it in hardware, and it'll work very well. So what I've done here is I've generated a LUT, or as it's known, a lookup table, which basically holds all the values of the duty cycles, because basically, as I said, right, you want to vary the pulse width, that is basically varying the duty cycle. So you can pre-calculate this. There's a formula. I would go too much into the maths, but basically you can generate this lookup table and keep feeding these values every, your carrier period. Depending on that, you generate a timer interrupt and you keep feeding these new values into your register, which will subsequently, drive the switches and generate the sine. So I have my lookup table here, and since I'm doing a 50 kilohertz carrier and a 50 hertz fundamental, it's going to be 500 if you just divide the carrier by this. So we have a 500 value lookup table, and if I just go down here, every time the interrupt is generated, we feed in a new value, the next value, into the register, and we keep cycling through this, and that's how the sine is generated. And this is for bipolar, so we're generating two complementary signals, which means one is your main signal and the second is your complementary signal, and you feed that to the diagonal switches. So I'll just show you the hardware now, and let's see how the sine looks. So I have my microcontroller here, the board, and here I did not mention it in the video, but since I'm doing just open loop right now, I have put these optocouplers here, and you can see the earlier video on it. It just provides isolation to protect your microcontroller from the power circuit. So since we have two PWM signals, I have two optocouplers here, the 6N137s. These are high speed optocouplers, and you need high speed because we're switching in a couple of tens of kilohertz, right? So don't use the slow ones, they'll destroy your PWM signal completely. So I have the two optocouplers, and after that we have the gate drivers. We need two, since we are driving two half bridges, we need two half bridge drivers. So it's the same one, the IR2110, and the PCB is ready as before. I've etched it a while back, so I have two of them. So they go from these optocouplers to this, and after that, this PCB is new. I basically made a edge bridge PCB, since again putting this on a breadboard was becoming a hassle, and all the breadboard parasitics were really messing with the circuit. So I just designed a PCB, and I etched it. So we basically just going roughly through it. We have this side, the screw terminal is basically our supply input. I'm getting it from the supply, and the gate drivers, and this supply is basically for the power circuit, the actual inverter. And for the gate drivers, I have a separate 12 volt, same from the wall brick, so that we keep the two supplies separate. But you do need to ground, we need to have a common ground. Since there's an optocoupler, the microcontroller ground is completely isolated from the power circuit. So other than that, these two grounds are common, the supply and the wall brick. So other than that, in the edge bridge PCB, we have the DC bus capacitor. It's 2200 microfarad. Another 100 nanofarad in parallel with that, just for high frequency noise and all. And that's a bleeder resistor, which makes sure that your capacitor discharges after you turn off your circuit. And those are the actual four MOSFETs. We have one leg here, and another leg is here, two MOSFETs. So I have heat sinks on them, so it can dissipate a decent amount of power. And these resistors are basically just the pull downs and the gate resistors. We need them, so they are here as well. And finally, these are the headers, which are the gate signals, male headers, which are coming from the gate driver. Same on this side, so two sets. And finally, on this side of the screw terminal are the AC, the output, and that basically goes using these crocodile cables to the load. And currently it might look a bit messy since I have my oscilloscope plugged into it, but if I just tell you, this is the LC filter. As I said, we need to filter the output, right? So LC filter, which consists of an inductor here, it's a drum type one, this black color one. This capacitor, blue color, it's below the load, which is our 100 ohm load, resistive load. So this inductor is basically 1 millihenry, and the capacitor is 1 microfarad. So that roughly gives you a cutoff frequency of around 5 kilohertz. And since we're doing 25 kilohertz switching, it's decently, the cutoff is below it. So our output should look pretty good of a sine, and it should attenuate the switching and retain the 50 hertz fundamental low pass filter. And since it has two energy storage components, the inductor and capacitor, it's a second order filter. So it has a slope of minus 40 decibel per decade. If you want to know more about that, you can see the filters video which I've done before. So yeah, now that the wiring is shown, I'll just switch the power circuit on, and what we'll do is first we'll look across the edge bridge. That means just the output without the filter. So before the filter stage, if I just stop this oscilloscope and show you, you can see that it's still a square wave, and these are the switching ripples and all of that within that. But roughly you can see that the period is 20 millisecond, which means the 50 hertz. But we want a sine wave, right? We don't want a square wave, so that's why we have the filter, right? So I'll just move this oscilloscope probe across the load now, instead of across the before the filter, and then you'll see the actual waveform. And yeah, now I've moved the oscilloscope probe across the load, and you can see that the output is a beautiful sine wave we synthesize. So that's exactly how the SPWM works. Since we attenuated the switching component now, we only have the 50 hertz fundamental left, and of course you can still see there's a bit of a ripple, because as I said, it's not a very perfect filter. You can probably make the capacitor or the inductance higher. I'll experiment with that later, but roughly you can see that it's clearly a sine wave, and this is the switching ripple which has still gotten through. And yeah, other than that, it looks pretty good as a sine wave. The period is 49, roughly 50 hertz, and the amplitude itself, you can see RMS around 8 volts, and peak to peak 24, which makes sense because you have plus 12 and minus 12. So yeah, roughly 24, 23 volts. And yeah, that's the RMS voltage, and that's the actual one which we are looking at, RMS. So roughly 8 volts, which is good. And yeah, that's how bipolar SPWM is working. And as you saw the waveform before this, the output was directly switching between plus 12 and minus 12. So that's why it's bipolar. So now we'll move on to unipolar. And as I showed it in the picture before, now we'll have two references. So one SPWM waveform that will be generated will look like this, and this is the main waveform, and the complementary of that, which will drive the bottom switch. This will drive the top switch, and this will be the second PWM, which will be found by comparing the second sine, the blue color one. So you can see sort of that here, this is the peak, right? It's reached maximum width. So roughly 180-degree phase shifted, it's repeating. So you can see that this is repeating here. So yeah, that's the phase shift part of it. And this will drive the top switch, and the complementary of this will drive the bottom switch. So in code wise, if we look, it's not very different from the bipolar one. The only thing is, now if we look at our pin out, which I didn't show before, we earlier had timer 1 channel 1, right? And along with that, timer 1 channel 1N, which is the automatic dead time complementary output, which you can configure here. I won't really go into those details, but yeah, that's the two PWM channels which we were using to drive our opto, right? So now we need another channel. Since now we need 4 total PWM outputs, we can use timer 1 channel 2, like I'm doing here, and along with that, timer 2 channel 2N similarly. So now you can see we have 4 PWM signals basically. And going into the code, the lookup table remains the same. I'm still doing 25 kilohertz, but now since we have to generate 2 outputs, if I just go into the interrupt code of it, what we can do is, earlier we had the running, right? You start from 0 of the array, which is basically your lookup table, go all the way up to every single time the interrupt is generated. We keep moving, that means we keep incrementing and putting the new value into the capture compare register. Now we have to handle 2 capture compare registers. So we want the 180-degree phase shift, right? So what we can do is, basically just if this, whatever this index is, assign that second index to be half array ahead of it, if that makes sense. And that, because 360 degrees is represented by the whole lookup table, right? So one half of it represents 180 degrees. So if we just shift this capture compare by half array ahead, that can be comparable to just doing a 180-degree phase shift. So that's exactly what we do here. We're shifting it ahead by half, and then again we have to wrap it around, right? Otherwise, if you try, let's say the array is 500 values, right, as I showed, earlier over here we have 500 values, right, over here, the capture compare values. So if you try to access the 650th element or something, it's going to, it won't give you an error, but it will just grab some garbage value and it will fill your PWM with that, and yeah, that can destroy your PWM. So that's why you need to wrap this around. That means, let's say the output after adding this, it becomes 650, then you just do 650 minus 500 in this case, and you get back 150. So that's the correct, because it's cyclic, right, it has to repeat. So that's why we do this. And then yeah, just fill the two capture compare registers, and same as before, once the first index reaches the end of the lookup table, we wrap around and start from 0. So that's it code wise. And I'll just go into the hardware circuit once. Everything else remains the same. The edge bridge board, two drivers remain the same, but earlier what we did was we gave the parallel outputs to these, right? That means the ln of this is same as hn of this high side, and ln of this is same as hn of this. So that's what we did last time, right? So what we do this time is we independently control all four channels. That's why I have added two more optocouplers. Earlier, there were only two, right? So now there are two more, and now all four of them are going from the microcontroller to the optocoupler, and the outputs are individually going to each of the gate driver pins. So there's no giving the diagonal to this and this anymore. So now independently we controlling all the four switches. So I'll just turn it on, and let's, same as before, 100 ohm, 1 millihenry and 1 microfarad filter. So before looking at the final filtered sine output, same as before, let me just show you the unfiltered output, and now you will see how the levels increased now that we're doing unipolar and not bipolar. Yeah, and now if I just turn everything on, I have the supply on and everything, you can roughly see, even though it's moving, my oscilloscope probably is not able to analyze it very well. If I just stop it, you can clearly see that the output is switching between plus VDC, minus VDC, and also there's a 0 level. This is the extra part which is added since we're doing unipolar. There's a 0 volt level. If I just stop this, you can clearly see it comes down to 0 volt, then it goes down and does its minus V work, and then plus V work. So you can sort of see, right, that it's representing a sign better than the bipolar. Instead of directly going plus VDC minus VDC, it's going plus VDC 0 and minus VDC, and that's better for filtering. And now this actually, even though this frequency is not showing it correctly, now our load actually sees the double of the switching frequency. That means it sees 50 kilohertz rather than 25. So yeah, that's why our filtering becomes easier. And also the voltage stress on the MOSFETs here, it reduces by half. That means each instead of being rated for the full VDC, now it can just work for half VDC. So that's also another benefit of unipolar. Now I'll just switch this, and now you can see the final filtered output. And now I switched it, you can see the probe's position across the load, and if I just turn it on, you can see that we have a very beautiful sine wave here, and compared to the earlier one, it's much better. You can see it cleanly goes here, and even if I zoom in much more, the switching ripple is very less, since now the cutoff still remains 5 kilohertz, but the switching has increased to 50 kilohertz across the load. So it's able to block it, attenuate it very well. And we have, similar to last time, we have sort of 7.9 volt RMS, and yeah, peak to peak around 23 volts, same as before, and an exact 50 hertz. So this is unipolar SPWM, and yeah, that's the whole SPWM story of it. This one was a bigger project compared to my earlier ones, and as you can see already, these wires have gone all over the place. It's a wonder that it's working in the first place, but yeah, it took a lot of debugging, and this PCB really helped. So instead of, now you can imagine, if this, just the optocouplers take so many wires, now you can think if the edge bridge also was on a breadboard, how messy it would become. And there's no guarantee that it would work, because now we're in tens of kilohertz, right? Already putting this itself on a breadboard is pushing it a bit, but it's still going okay. But if you try to put your edge bridge on a breadboard, it's going to be disastrous, because all the parasitics are going to act up, and you might not even get something and heat up, blow up, whatever. So yeah, always some circuits, if you want them to if you're sure of the circuits and you have tested them before on a breadboard, you can always design a PCB or put it on a perf board, and then you can use it as a module. You don't have to worry about anything going wrong in that, as long as again you don't really drive it, you take care of the dead time and everything. So yeah, that's the whole Unipolar SPWM, and I hope you learned a thing or two. This is my inverter series. I'll keep following up on this, and yeah, thank you.